This is section 16.6 on parametric surfaces and their areas. So we are now up to page 1111. Near the end, parametric surfaces and the area. So for parametric surfaces, you have a function of two variables. So for instance, R, position vector involving u and v. Now, if you only have one variable like R of u or R of t, you get a three-dimensional curve. But if you are allowed 2 degrees of freedom, u and v, imagine spreading out in 2 dimensions, so you end up with a surface, R of u and v. So perhaps one goes this way and the other goes that way, and you generate a surface. So that's what we're dealing with. And there's lots of nice shapes. You can see them. I won't have you draw them. Okay, helix and stuff like that. Okay, but we'll just cut to the chase and get you what you need for exams and such. Okay, tangent planes. So if you're given a surface like so, how do you get a tangent plane? You notice you have an R of u and R of v. R sub u, R sub v. So if you have R sub u and R sub v, the cross product of R sub u and R sub v will give you a normal vector. Okay, so for example 9. In fact, if you want to put something like example 9 in your cheat sheet you made, it's probably the best example. If you give an x equals u squared, y equals v squared, z equals u plus 2v at a particular point, and so on. You compute R sub u, R sub v, and their cross product, okay? And then you plug in, and you will have a normal vector. Okay, and then once you have that, you can use the formula for the tangent plane. Okay, so that's that. A surface area, formula on page 1117. You have R of u and v. Surface area is a double integral of the magnitude of RU cross RV dA. Again, RU cross RV, the cross product magnitude gives you the area of the parallelogram determined by the two vectors. Okay, this is sort of like a Jacobian again. So if I go from one coordinate system to the other, from UV to XY, let's say, okay, the so-called Jacobian is RU cross RV. RU is partial of x with respect to u, partial of y with respect to u, partial of z with respect to u, and RV similarly, partial of x with respect to v, partial of y with respect to v, partial of z with respect to v. And we have the special case. If you have z as a function of x and y, and we've already seen this on page 1118, but if you want to put it again, you may. Area is the square root of 1 plus partial of z with respect to x squared plus partial of z with respect to y squared dA, because that's what happens when you have the magnitude of Rx cross Ry in this position situation here. All right, so how do we do some homework problems? Page 1120, 16.6. This, I'm not going to have you do a computer to generate the curve. Let's see, I don't think you have to do any of these either. Okay, find a parametric representation for the surface. Okay, we get to use some of those. So you get 25 in there. So I have to lift the book up sort of like that. A little bit funny, but I think you can read it. And so over here. Okay, tangent plane. Tangent plane. And some areas. All right. So problems 1 and 2. Okay, so R of u v is 1 plus u minus v, u plus v squared, u squared minus v squared. They're saying, is the point 1, 2, 1 on this surface? Well, I just try to solve it. I set that equal to 1, I set that equal to 2, and I set that equal to 1, and see if I can get a consistent equation. Okay, so this one, this says u plus v is 0, or u is negative v, or v is negative u. Okay, so if I plug in to say z, then I would get u squared minus v squared is u squared minus a negative u squared, which is the same as u squared minus u squared, which is 0. And that's a contradiction because z is 1. So the answer is no, it is not on the surface. Okay. On the other hand, how about 2, 3, 3? So again, 1 plus u plus v is 2. U plus v squared is 3. U squared minus v squared is 3. Okay, the x equation says u plus v is 1, or u equals 1 minus v. Okay, then I plug into here, 1 minus v plus v squared is 3. V squared minus v minus 2 is 0. Factors into v minus 2, v plus 1 equals 0. So v is 2 or negative 1. Okay, v is negative 1, v is negative 1, u is 2. The answer is yes, they all work. Okay, so if u is 2 and v is negative 1. So 2, negative 1, that gives me 2. 2, negative 1, that gives me 3. And let's see, 2 squared is 4, minus 1 is 3. So the answer to that one is a yes. Okay, 19, you're going from the origin 0, 0, 0, and then scalar multiples of 1, negative 1, 0, which is I minus j, and 0, 1, negative 1, which is j minus k. Okay, so what the problem says. So it goes through the origin, it contains I minus j and j minus k, problem 19. So I have the origin and a scalar multiple, u, of I minus j and v of that. So clean that up, x equals u, y equals negative u plus v, and z equals negative v. 23, x squared plus y squared plus z squared equals 4. Above z equals radical x squared plus y squared. This is z squared equals x squared plus y squared. That goes up at a 45-degree angle. So I switch to spherical coordinates, except that I know that the radius or rho is 2. So x is rho 2 sine phi cosine theta, y is 2 sine phi sine theta, z is 2 cosine phi. And you got this part over here. So theta is from 0 to 2 pi, it's going all the way around, but phi is going from 0 down to pi over 4 in that particular case. 25, x squared plus y squared plus z squared equals 36. That has a radius of 6. Z is between 0 and 3 radical 3. So I want to find out where they touch. So if I plug in z is 3 radical 3, that means z squared is 27. So you have x squared plus y squared equals 9. So up here at z equals 3, I have x squared plus y squared equals 9. Okay, which means the radius is 3. This would be 6. That's 3. That's 6. So that makes this angle right here equal to 30 degrees. The side opposite the 30-degree angle is half the hypotenuse. So that's 30 degrees. So pi over 6 is what you have. So again, I have x is rho 6 sine phi cosine theta. Y is 6 sine phi sine theta. Z is 6 cosine phi. Theta is going from 0 to 2 pi, but phi is only from here to here. So that would be pi over 6 to pi over 2, between pi over 6 and pi over 2, because this would have to be a 30-degree angle. Okay, 33, tangent plane. X is that, Y is that, Z is that, 2, 3, 0. So what's the U and the V? Well, U minus V has to be 0, which means U and V are equal. So if U and V are equal, then and X is 2, then they're equal to 1. So U and V are 1. Okay, so R sub U, differentiate with respect to U, 1, 6U, 1. R sub V, differentiate with respect to V, 1, nothing, negative 1. Take the cross product of RU and RV. So IJK, 1, 6U, 1, 1, 0, negative 1. So that minus that is negative 6U. The opposite of negative 1 minus 1 becomes a positive 2. And then the K component is nothing minus 6U. So negative 6U, 2, and negative 6U. Plug in U as 1 and V as 1, you get negative 6 to 6. Or you can have any scalar multiple of that. So since this is a normal vector and you're allowed to take any scalar multiple, it's easier to take negative 1/2 of that, which is the vector 3, negative 1, and 3. So 3x minus y plus 3z equals k. To find k, I plug in for the point 2, 3, 0. So I put a 2 here, a 3 here, and a 0 here. 6 minus 3 plus nothing is k, so k is 3. So the equation on the tangent plane is 3x minus y plus 3z equals 3. All right, 37. They're telling me u is 1, v is 0. Plug in, that gives me x is 1. Remember, r is a position vector. 2u sine v, well, sine of 0 is 0. And 1 cosine of 0 is 1. So plugging in, I get 1, 0, 1. Okay, r sub u, differentiate with respect to u. 2u, 2 sine v, cosine v. R sub v, differentiate with respect to v, nothing. 2u cosine v, negative u sine v. Cross product. So ijk, 2u, 2 sine v, cosine v, 0, 2u cosine v, negative u sine v. So the I component is that minus that. So that's negative 2u sine squared minus 2u cosine squared. And if you factor out the negative 2u, you get sine squared plus cosine squared, which is 1. So it's just negative 2u. J component is the opposite of negative 2u squared sine v minus nothing. The k component is 4u squared cosine v minus nothing. And I plug in u as 1, v is 0. Okay, so if I plug in, let's see, u is 1 and v is 0, put a 0 there, that's 0. And let's see, put a 1 here and a 0 there, you get negative 2. And v is 0, that makes that 0. And 4, plug in 1, plug in 0, you get 4. And again, it's easier to pick, let's say, negative 1/2 of that, or 1, 0, negative 2. So x minus 2z equals k. Plug in the given point 1, 0, 1. Okay. So 1 minus 2 equals k, or k is negative 1. So x minus 2z equals 1, or negative x plus 2z equals 1. It's a little bit cleaner. All right, surface area, 3x plus 2y plus z equals 6 in the first octant. Solve for z. Z is 6 minus 3x minus 2y. That means z sub x is negative 3, z sub y is negative 2. Okay, so in the xy plane, 0, 3, 0 is just 0, 3. 2, 0, 0 is 2, 0. A little bit of algebra. Y equals mx plus b. The slope is negative 3/2. So y is 3 minus 3/2 x. So the area of that surface triangle there is the square root of 1 plus z sub x squared plus z sub y squared dA, which is radical 14, area of the triangle. Area of this triangle is 1/2 base times height, 1/2 of 2 times 3, so 3 radical 14. 43, z is that, 0, 1 cross 0, 1. So z sub x is x to the 1/2, z sub y is y to the 1/2. Double integral of 1 plus z sub x squared is just x, and square root of y squared is y. All right, so 1 plus x plus y to the 3/2 divided by 3/2 is times 2/3. Plug in y is 0, and y equals 1. Plug in y is 1, 2 plus x to the 3/2 minus plug in 0, 1 plus x to the 3/2. So it's a little bit clumsy. So integrate again. So 2 plus x to the 5/2 times 2/5 minus 1 plus x to the 5/2 times 2/5 from 0 to 1. Plug in 1 here, you get 3 to the 5/2, and that's minus 2 to the 5/2. Plug in 0, you have 2 to the 5/2 minus 1 to the 5/2. So it's like that. So it's 4/15, 3 to the 5/2 minus 2 times 2 to the 5/2, which is 2 to the 7/2. It's minus 2 to the 1 times 2 to the 5/2 plus 1. Okay, we can leave it like that. 47, y equals x squared plus z squared inside x squared plus z squared equals 16. Okay, so y sub x is 2x. Here, y is a function of x and z, so we're not used to that. But you can just switch the letters around. If you have z is a function of x and y, and make that x squared plus y squared equals 16, the answer is exactly the same. Okay, so radical 1 plus 4x squared plus 4z squared dA. Switch over to polar coordinates. 1 plus 4r squared r dr d theta. This is a circle of radius 4, so r is going from 0 to 4, theta from 0 to 2 pi. The derivative of this is 8, so 8 inside, 1/8 outside. This is a constant, does not depend on theta, so take out the 2 pi, 1/8. So that's 1 plus 4r squared to the 1/2. So when you integrate, it becomes the 3/2 power times 2/3. So this comes out to be 4 over 24 pi over 6. Plug in 4, you have 65 to the 3 halves. Plug in 0, you have 1. Or pi over 6, 65 radical 65 minus 1. And 49, parametric one. X is u squared, y is uv, z is 1/2 v squared, u going from 0 to 1, v going from 0 to 2. So this time I have to use the RU cross RV formula on the surface area on page 1117, this guy here. All right, so R sub u, differential with respect to u, 2u, v, 0. R sub v, differential with respect to v, nothing, u, v. Take the cross product, ijk, 2u, v, 0, 0, u, v. So the I component is v squared minus nothing. J is the opposite of 2uv minus nothing. K is 2u squared minus nothing. Okay, the magnitude of RU cross RV is the square root of v to the 4th plus 4u squared v squared plus 4u to the 4th. Very conveniently, this is v squared plus u squared squared. So the square root is just v squared plus u squared. So that's what I'm integrating. So 0 to 1, 0 to 2, u squared plus v squared, du dv. Integrate with respect to v, u squared v plus v cubed. Integrate with respect to u cubed over 3 plus u v squared. Plug in 0, you get 0. Plug in 1, 1/3 plus v squared. So 1/3 v plus v cubed over 3 from 0 to 2. Plug in 0, you get 0. Plug in 2, 2/3 plus 8/3. Final answer is 10/3. All right, so that was section 16.6.